Okay.
Okay.
Okay. Well, welcome. It's been a month to the N3C Community Forum, October 23rd. And next slide. And we have Emily Pfaff. So it will be recorded as it always is. Use the Q&A button to post your questions as you always do, or raise hand to unmute your microphone. Next slide. And we've got 8.2 million COVID cases and 20 million people in the database. Next slide, please. And so November 27th, hormone replacement therapy in COVID-19 solid organ transplant recipients compared to the general population by Amanda Vissen. And Peter Leese will be talking about CMS and EHR data examples December 11th, and November 13th is TBD. Okay, so without further ado, we have our own Emily Pfaff, some very interesting work involving developing machine learning phenotypes involving N3C-RECOVER validated by all of us. So that's very intriguing and very timely, given the progress made along those lines by Emily and group. So Emily, over to you.
Sure thing. Give me just 1 second to share slides. Can you all see the slide view?
Yeah.
Okay, wonderful. So it's been a while since I have spoken at the community forum, so I'm very happy to be back today. And today I'm talking about something that we really enjoyed working on last year, which was taking our long COVID machine learning model, which I have spoken at community forum about in the past, and actually trying to use it outside of N3C. I think it's really important that we do more work like this and that we encourage more work like this, because it's one thing if you build a machine learning model that works in your own data, and it's a totally other ball of wax if you can build one that works outside of your own data. And though I think that we did have a successful transfer here, and I'll talk about that, it wasn't a super easy or straightforward process. And so we learned a lot of things along the way that I am really hopeful that we can apply to other projects, and maybe that you can apply as well. So without further ado, I'm not going to spend a ton of time talking about long COVID in general. It's a very important topic. It's something that clearly those of us who are participating in RECOVER spend a lot of time thinking about. But we have spoken about it a lot on community forum in the past. But I am going to just remind folks why it's really difficult to find patients with long COVID in the EHR, and moreover to give a rationale as to why a machine learning model is necessary in the first place. For those of you who work on computable phenotyping problems, whether it's COVID, whether it's diabetes, whether it's anything else, you know that certain diseases are pretty straightforward to phenotype using diagnosis codes, using lab values, using other factors. And some conditions present much bigger challenges, and long COVID is in the much bigger challenges bucket. And I have this Venn diagram here to sort of show that there's a pretty big gap between what is actually documented in the EHR for patients with long COVID and what the experience of the patient with long COVID is. And long COVID is by no means the only disease for which this is the case, but it is a pretty widespread example. And so, you know, patients are experiencing really disabling symptoms, lowered quality of life. They're often on, particularly in the beginning of the pandemic, perhaps and hopefully less so now, but on a diagnostic odyssey to get anyone to even believe in that they're experiencing these symptoms and that their symptoms are a result of COVID. And they also are really lacking opportunities to record the trajectory of their improvement or the lack thereof, particularly patients who have been dealing with long COVID for literally years now. On the other hand, clinical documentation practices, we thrive on ICD-10 diagnoses, which sort of tie up diseases into a neat little box because we really rely on those structured codes to do so many things. Obviously, anything that gets billed, we have access to, lab results, prescriptions, vital signs. These are very structured data elements that we can use as clues, but it really is not terribly aligned with the actual experience of having long COVID. Moreover, there are really important long COVID features. High on that list would be things like brain fog or post-exertional malaise that just are not recorded in the EHR. If they are recorded, it is in the free text note. And it's not to say that one cannot get at the information in the free text notes, but for most purposes, it is more straightforward to use the structured data. And so that's what we're going to focus on today. And then I always like to offer the caveat that EHR data is, of course, only available for patients who have access to or choose to seek care. And a lot of patients with long COVID, as I have been told by our patient advocate representatives on Recover, got so understandably frustrated in the beginning of this long COVID diagnostic odyssey that they just sort of gave up seeking care. And because of that, we are lacking data on those folks. And there are a ton of people out there that have long COVID that we just don't have represented. However, so I just offered a bunch of sort of not super hopeful descriptions of the problem here, but I do think there is a bit of a however with N3C specifically, because we do have some affordances that would not necessarily be available in a local EHR data set. One is that we have a very large, diverse, nationally representative population, which helps. We are certainly not grabbing everybody, but it is a much larger set than is available at any one site by a long shot. We have data from many clinical sites. This slide actually needs to be updated. It's now 82, not 78 sites. So, very, very wide variety of sites that are contributing. So not only do we have a lot of patients, but we also are not getting stuck in idiosyncratic patterns of clinical documentation practices that occur at any one site. We have lots of different idiosyncratic patterns that are all put together, and we can sort of average those out in N3C. And then finally, we have a nice volume of longitudinal data. So certainly not every patient, not even close, has data all the way from 2018 to present, but many patients do. And so we're able to look historically and really use that to our advantage here. Okay, so in the beginning of looking at long COVID, we had no ICD-10 code to work with at all. And so we were really just looking for anything to hang on to. And it kind of felt like we were trying to just climb a huge, smooth, slippery ice wall. There was nothing even to grab onto. And because of that, we had to use proxies in order to even try to train a machine learning model to recognize long COVID. The proxy that we used originally was use or attendance of a long COVID specialty clinic. And we did have data from a subset of our sites that provided that information to us. And that we called that a silver standard, maybe a bronze standard for who had long COVID, certainly not a gold standard, but we did use that in the absence of more structured information. And that the first version of our model, the version that was published, that's what it was trained on. In October of 2021, UO9.9 was released for use in the United States. And that is the official ICD-10 code for post-COVID condition unspecified. Note that it is not long COVID or PASC. It is a very generic name, and I think that led to some strange usage of UO9.9, as we'll talk about in a second. But it existed, and that gave us something to grab onto. And as time went on, use of UO9.9 increased quite a bit. And so in the beginning, when it was first released, it was very sparsely used. And as time went on, it became much, much more common. And at this point, we have tens of thousands of patients in N3C who have that code, which really gives us a lot to work with. So this code is handy because we can characterize patients who have a UO9.9 in that we look at that UO9.9 and we can see other stuff that sort of makes a pattern across patients that have that diagnosis code. One being other diagnoses and comorbidities that seem to go along hand in hand with UO9.9, medications that these patients are on, procedures that are being ordered for these patients, lab results, etc. And these patterns not only enable us to do descriptive analysis, which that linked to one of our BMC medicine publications. That's exactly what it is a descriptive characterization of patients that have UO9.9, what else is going on with these patients. But those patterns also enable a machine learning model to learn about what a UO9.9 patient looks like and can then apply those patterns elsewhere. So that is the amazing advantage of now having an ICD-10 code. However, there are some disadvantages to using UO9.9. And I really particularly want to stress this because a question that we've gotten a lot, an understandable question is, well, now there's an ICD-10 code. Why do you need to build a machine learning model at all? Just do what we do when we are, say, phenotyping diabetes and just use patients that have a couple of occurrences of the relevant ICD-10 code and move on with your life. There's nothing wrong with doing that, except for I would suggest that it is not nearly inclusive enough. And that's really what the machine learning model is attempting to fill. Number one, there are equity and access issues that I touched on earlier around UO9.9. We discovered in our descriptive analysis that the patient group with UO9.9 assigned on their record is disproportionately white and non-Hispanic and is significantly less likely to live in areas that have higher social deprivation. So there is clearly some pattern of lack of access. And the hypothesis is that it's not that there's anything about those patients that makes them more likely to have long COVID, but there is something that makes them more likely to be labeled as having long COVID. So that's something we need to keep in the back of our mind at all times. There are weird usage issues with UO9.9, and I suspect that this has to do with the fact that it is a newer code. So the guidelines for when you should use a code are not always clear, or even if they're clear, they're not always disseminated broadly enough. And so we see strange patterns such as UO9.9 codes that appear to occur on the same day or very shortly after a positive COVID test. It's not to say that couldn't happen, because you could have had COVID a long time ago and this is a reinfection, but it happens often enough where we're suspecting that there is some misuse going on, meaning that not every UO9.9 case is a true positive. And then maybe the most wide-ranging issue is the timing issue. Because UO9.9 came out in late 2021, there are vast numbers of patients who have long COVID from earlier in the pandemic that missed out on getting that code. And we don't want to put ourselves in a position where we never find those people. And so, I ran some numbers when I originally made these slides a couple of months ago and noted that if we assume that only patients with a UO9.9 code had long COVID, it would look like of COVID positive patients in N3C, the long COVID prevalence was around 1% or even less. And that just feels misleading. It's far, far too low. We're clearly missing people. We've got advantages of UO9.9. We have disadvantages. I would suggest that the disadvantages are disadvantageous enough to demand using other methods. And that other method for us is machine learning. So here's our alternatives. Some of you have probably seen this slide before. Our machine learning model is something that I would call still imperfect, but more inclusive than what we were just talking about. So we train the machine learning model on the EHRs of patients who are labeled long COVID positive. And we have changed what that looks like throughout the years. We have iterated on this model several times now. It no longer looks like what it looked like when we first published this. Currently, as of today, what we are using to label a long COVID case is somebody that has at least 2 UO9.9s to get away from some of that strange usage pattern issue, or has at least 2 long COVID clinic visits. That if we used to apply those criteria, we would have ended up with a very, very small group of patients. But now at this stage in the pandemic, that is still tens of thousands of patients that can be used for training. And so that is our current training set definition. The machine learning model, which is an XGBoost model, learns patterns of clinical features of those patients in the training set. And those things include things like dyspnea, fatigue, lots of outpatient visits, new prescriptions for albuterol, new prescriptions for corticosteroids, etc. And then we can then apply that trained model to everybody in N3C and identify previous unknown cases using these learned patterns. And it's not that the model spits out a, this person has long COVID and this person doesn't. Instead, what it gives is a predicted probability score for this person looks, 70% likely to have long COVID in my estimation. This person looks 30% likely, and leaves the humans involved to determine what the rate threshold is for us to say, yeah, we think that's a true positive or not. I will say that one of the exciting developments that I'm not going to talk about today, and maybe we'll talk about in a future community forum, is that we are currently revising this model to not even require any EHR documentation of acute COVID infection. We no longer believe that should be a prerequisite for the long COVID computable phenotype because home testing is so prevalent. Home testing is making it so that a lot of people have had COVID maybe multiple times, and it's never recorded in their EHR. And yet in their EHR, we are considering that person not long COVID. That's problematic. So exciting things to come with this model. Okay, so we make every effort to avoid black boxes. We really want our model to be explainable. And to make it explainable, we report feature importance so that any user of the model can look to see what the model is using to make its predictions. We open source all of our code for maximal transparency, so anyone can go in and see exactly what our model is doing at all times. And as you saw from my spray of caveats before we got to this point, we're very upfront about the limitations of models like this. But there is this concern that you can build a machine learning model and it can work pretty well on your own data, but until you try to run it somewhere else, can we really say it's shareable until we've tried to run it out of N3C? And that's exactly what we aimed to do last year. So enter our friends at All of Us. I am not going to define the All of Us study itself. It is a huge topic. It's a wonderful study. We love being involved with it. I would definitely encourage those of you who are not up on All of Us to go investigate the study and maybe even join the study. I'm a participant, and it's been really nice as both a participant and someone working on the actual study itself. Their goal is to build a research program that has data for 1 million people. And right now they have EHR data from over 50 organizations, and conveniently it is stored in the OMOP format. They provide analysis tools for researchers in their researcher workbench. And for all of these wonderful reasons, they were really a perfect test bed for the N3C long COVID machine learning model. And here is a list of some of the folks that were involved in this project. And one thing that I really love about this is that there were so many people from lots of different places. We had N3C folks, we had RECOVER folks, we had folks from the All of Us DRC at Vanderbilt, we had collaborators from PCORNet. This was a real team science effort, and it was very fun. Okay, so here's what we did. In N3C, we did what we always do when we run the model, which is that we identify a base population that qualifies to get a model score. And this was using the model prior to the current version where we're investigating not requiring an acute COVID date. And so in the case of this experiment, we're looking at adults who have some kind of acute COVID date on record, whether it's a diagnosis code or a positive test, and they have at least 145 days of follow-up available since acute COVID, and it has to have at least one healthcare visit in that 145-day period. We took the code that we used to identify that base population, which is in itself a computable phenotype, although not one for long COVID, and we posted that on GitHub. So that was sort of the first piece of sharing this code. We then ran the train model, again, inside of N3C on our base population, like we always do, to get a model score on each patient. So we've done this hundreds of times now. This was just one other time. But then what was different is that we took all of that code that we used to engineer features and run the model, and we exported all of that out as well and posted it on GitHub. So all of the code used to do our model process from identifying the base population to getting model scores is now up on GitHub. At that point, our friends at All of Us started to reconstruct that base population identification pipeline using our N3C code, take it down from GitHub. And then they reconstructed all of the feature engineering steps that using the N3C code that we had put on GitHub. And they had to, and I'll talk about this a little bit more in a second, but they had to do a lot of work to make that work on their end. And that in and of itself was a lesson learned here. But Critically, they did not retrain the model. They used our pre-trained model in their data. And I will talk about why they did that and why we very purposely did that in just a moment. And then finally, they assessed performance based on the few patients in all of us that have a U09.9. So when you're assessing the performance of a machine learning model, there's lots of complexity to it. There's lots of different ways you can do it. But here, we were using patients with U09.9 in all of us as a gold standard, even though we know it's a silver standard or maybe a bronze standard. And the idea was that let's just see how often N3C's pre-trained model, not retrained on the all of us data, can find the U09.9 patients that are in all of us. So that's how we assess performance. Okay, so here were the sticking points. Number one is it is really hard to share a machine learning model. Now, it was really cool that our team sort of had dedicated time to do this, protected time to do this, because we met really frequently over the course of 12 weeks to share knowledge and troubleshoot with each other. And that really made all the difference. I don't think we would have been able to do this nearly as successfully if we had just never communicated and all of us had just sort of taken the code and ran with it and we never spoke to each other. There were some technical barriers. So N3C Enclave uses PySpark and SparkSQL as sort of languages of choice, and all of us uses Python and Google BigQuery. So all of that code that I talked about needed to be translated from one language to another, similar language, prior to use. But one benefit of this is that all of that code that the all of us folks worked so hard to translate, we actually got that pushed back up to our GitHub as a community contribution. So now if somebody else wants to use the model, they can either use the PySpark SparkSQL version or they can use the translated version. So, you know, that's an open source success. For those of you who are familiar with macro visits, or the concept that we use in N3C to sort of tie different visits together into an inpatient visit, even if it's not labeled an inpatient visit, that is not standard to OMOP. That is an N3C thing, but we rely on it very heavily. And so we figured out, you know, halfway through this process that we also needed to open source the macro visit pipeline in order to make this work. So we did that too. So now macro visit pipeline is on GitHub as well, which again, I think is a benefit to the community. Probably the biggest problem that we ran into was feature mismatch. So there were several important features from the N3C model. And when I say important features, what I really mean are diagnoses. Diagnoses that the model relies on heavily to make a decision were simply not present in the all of us data. All of us, I believe, had around 9,000 patients that had some record of having COVID, and N3C had in the millions. And so naturally, there was a wider variety of conditions associated with the N3C patients than the all of us patients, because there were just so many more of them. So we ended up with a lot of missing features in the all of us set, which I do think sort of impacted the results of the experiment. And then finally, I just want to stress that if code runs with no errors in somebody else's data, that doesn't necessarily mean success. You can get something to run successfully and the results can still be bonkers. And so to avoid bonkers results, our teams, again, in the course of our frequent meetings, we compared assumptions about the data to always ensure we were comparing apples to apples as best we could. Okay, so a result summary here. This is a table straight out of the publication that we put out about this, where you can see that the number qualifying for model inclusion criteria, or our acute COVID cohort, N3C has over 2 million, all of us has 9,000, pretty big difference there. An even bigger difference is that at the time, we had about 14,000 U09.9 patients in N3C, whereas all of us had 30. The performance is different between the two. So we had an area under the receiver operating characteristic, a curve of 0.83 for N3C and 0.72 for all of us. And critically, as I just mentioned, we have 200 features in the N3C model, but all of us was missing 39 of those. And so they have 161 features in their model. These are some of the most important features. In the interest of time, I'm not going to go through all of them, but things like dyspnea, fatigue. This is how often people are using outpatient visits, how often people are using inpatient visits, whether they were hospitalized with COVID or not, and on and so forth. They all sort of passed the sniff test. We feel like this model is pretty explainable, but there were a couple of things, even from this list, that were missing in all of us. And I do think that may have led to some of the performance differences. Oops. Next slide. Need to be stuck. There we go. So this was also interesting and instructive. What you're seeing here is a distribution of the predicted probability of long COVID across the N3C cohort on top and the AOU cohort on the bottom. So you can see that, as you would expect in the N3C cohort, most people have really low model scores because they don't have long COVID. And some people, a smaller amount of people, have really high model scores because they are likely to have long COVID. Interestingly, in the AOU cohort, and we have some theories as to why this is, the lowest scoring bucket was a lot smaller than we expected, but then started to follow the trend, which was interesting. And then the other sort of oddity was that the highest scoring bucket was larger than we expected. And so this was a bit of a head scratcher, but we did have some theories as to why this may have occurred. So number one is that there are quite different demographics between N3C and AOU. Now, N3C includes everybody with COVID from those 82 sites plus matched controls. AOU is a consented patient population with a purposeful focus on diversity. And I will show you how different the sort of breakdown by various demographic metrics is between the two cohorts. Therefore, those consented patients in AOU may have hidden differences from people who, it's basically a convenient sample in N3C. And it's really intriguing to consider the implications of translating a model that we generated on sort of pure real world data to real world data that is obtained from consented patients. Those consented patients, just as an example, and this is speculation, by the way, but as an example, might be different in that they may be more engaged in their healthcare in general. They may use healthcare a lot more often than the average person. There's a lot of possible differences that we weren't able to sort of get at in a way that made us feel 100% sure, but it was clear that the cohorts differed quite a bit. I do think those missing features have a lot to do with the different performance in that, again, all of us is missing 39 of the 200 features, and 2 of them, tachycardia and diarrhea, were in that top 25 list that you were looking at on the last slide. And so it was essentially, it was disadvantageous to the AOU run because it was missing a lot of important clues. Now, it certainly had 161 good features, and we think that still resulted in a successful run, but this is certainly something to keep in mind for future model transfers. And then finally, all of us updates a lot less frequently than N3C, and this meant that there was a lot less follow-up available, and there was also just a less longitudinal time available. So that was part of the reason that all of us at the time only had 30 patients with UO9.9 in the repository, because they did, I believe at the time, the data had only been able to capture a few months of UO9.9 even being available for use. So, you know, we went back and forth and sort of brainstormed these potential explanations for the differences that we saw. And just to show you, I won't walk through this whole table one, but this is the N3C population. And if you look, basically, like if you look at the race breakdown and the ethnicity breakdown, it actually looks a lot like the race and ethnicity breakdown of the United States as a whole. Whereas if you look at, oh, and by the way, this is divided between people who got lower model scores, people who got medium to high model scores, and people who got really high model scores. So the demographics are a bit different among those 3 categories. But mostly I put this in here to illustrate that, for example, here, there is a much higher number or percentage of non-white participants in AOU. And of course, the numbers are much smaller because the size of the cohort is a lot smaller. So, you know, this really is food for thought and sort of some of the things that may be causing the differences in performance that we see. And also sort of makes us think about what biases, the hidden biases or obvious biases, perhaps, that the model is maybe holding on to. So lots to think about there. Quick note on performance assessment of these kinds of models and why it's so hard. So all of you are probably familiar with how to calculate sensitivity and specificity. And indeed, we can, you know, show our ROC curves here. So the N3C cohort ROC curve for the model is on the left, and the one for all of us cohort is on the right. Looks a little shakier because the performance wasn't quite as good. But diagnostic classifiers like this one have a huge problem. We don't know that a person who isn't labeled as having the disease, in this case having a UO9.9, doesn't have the disease. We have no way of knowing that. So that means that everyone that the model identifies as a yes, as a high scoring person who is not labeled with a UO9.9 is considered a false positive when you're doing performance assessment. But that isn't really what we want. What we want is to enable, we sort of want to encourage the model to perhaps label people as highly likely to have long COVID that don't have a UO9.9, because that's the point of the model. And the model does in fact behave that way. But when you're trying to use just regular performance assessment metrics that you would use for machine learning models, it becomes really difficult because of this sort of tricky philosophical problem. So in wrapping up here, the whole collaboration really had a lot of positive outcomes other than the ones that I just presented, the sort of scientific outcomes, in that we really think that this kind of collaboration should be a model for more model sharing exercises. Obviously we expanded our sample size by going out to all of us, but that wasn't really the point, right? Because N3C has a huge sample size. We didn't need more patients. What we needed was a new environment, a new test bed for our model, and that's exactly what we got through the collaboration with all of us. It did something that means a lot to me, and I suspect many of you too, which is that we were replicating and reproducing existing science rather than continually reinventing the wheel in lots of different research groups. And as far as we could tell, that really reduced the time requirement that it would have taken to build a new long COVID identification model in all of us, because we were able to use existing work and sort of a reduce, reuse, recycle kind of thing. This is not a slide that I made, but one that the All of Us team made. And it really shows that a traditional approach, it takes a long time to do this kind of work, right? It can take really, really long time. Our machine learning model development in N3C did in fact take years. So it also took a long time, but the Recover All of Us collaboration was just 3 months. And so that time is continually decreased by reusing work that's already been done. And we should just strive to do this so much more than we do in the field of informatics. So there's some opportunities from this. So again, I won't keep belaboring the point, but I do think this is a better paradigm for model sharing. I think sometimes people put their code on GitHub, and I've been guilty of this too, so this is not at all judgmental, but you put your code on GitHub, and because it's there, you say, oh, it's open source and shared. But I don't think that that really is as meaningful as putting a lot of effort into what you put on GitHub to make sure that it has documentation, and that documentation is straightforward, that the code is well commented so that people can understand what you're doing, and that you organize your GitHub repo in a way that somebody could walk in, and maybe not a non-expert, but somebody who's sort of familiar with the area could walk in and really understand what you're trying to do. I really want to normalize that in the field and say that your model isn't really shareable until you've done that. If you are a user of Researcher Workbench in All of Us, you can go use this today. The All of Us team did a great job putting this out there as a tool for their users to use. So go nuts, go have fun with it. And because it is open source on GitHub, if your site has OMOP and you want to use this at your own site, have fun. And if you do, please tell me how it goes. Just want to give credit to all of the wonderful team, again, from lots of different places. Everybody really did a wonderful job contributing to this. And with that, I think that is all my slides.
Great. Thanks, Emily. That was fantastic. So question from Josh Fessel, not a question, but a comment. So I guess it's a comment, Josh. It needs to be appreciated what a triumph of team science this effort truly is. As usual, Dr. Pfaff has done an outstanding job of making things crystal clear. Having a front row seat to this effort has been incredibly inspiring and a true privilege for me. The project, I think, serves as a high watermark for what is truly possible when teams get together. So I guess you could answer it anyway.
Thank you, Josh. Josh was a huge part of this and a real cheerleader for this effort. So that's wonderful feedback. Thank you.
It's great. And Cindy, who I'm curious if we retrained an ML model in All of Us, would the performance be better and how much better? My concern with pre-trained ML model and applying it to a new population would be that if the two populations are very different, it wouldn't be a good fit. There's also a question about which model should be shared. Is it always the earliest model, the largest model, or else?
Fantastic question. I'm glad you asked it because I thought I was going to come back to why we didn't retrain the model in AOU, and I neglected to do so. So the reason, as you may have guessed, is because there were not enough patients in AOU, particularly with a UN 9.9, to retrain the model at all. There were only 30 patients. And if you train a model on 30 patients, you're going to get weird behavior, overfitting, all that stuff you don't want. With that said, I do think that the performance would be better if the model were retrained in all of us. And so we really had a choice to make. We didn't have the option in this case of retraining the model. And so we ended up having to use the pre-trained model. And I think that some of those wonky performance upticks in the high scores and downticks in the low scores, that should be added to the list of possible explanations for that because the populations are so different. In terms of which model should be shared, one thing that I have not been good at in the past, and I'll make it a New Year's resolution to be better at it, is to not just put something out on GitHub to share it and then never update it again, which again, huge habit of mine. But as I said in the beginning of the talk, that model, even the one that we shared with all of us, we've updated it about 2 or 3 times since then. And that is something to consider when you're looking at how much effort these sharing projects take, is that it's very rarely a one and done thing. So, when it comes to which model should be shared, I think the answer is all of them, particularly if you're making it better over time, right? If you're doing something that makes your old model look bad, you should definitely reshare the new model. But does that mean that all of us is going to come and retranslate the code for the new model and update everything? It's a lot of effort, and we shouldn't take it for granted, for sure.
Yeah, and I think Emily and folks also in terms of validating models, I think it actually really is good practice to train on one data set and test on the other. I mean, understanding that the distributions may be different, but it's always confidence inspiring to do that. Although if you have a data set and you're going to really try to do something on an enterprise level with it, at some point you want to fine tune or retrain. But I think it also shows the robustness of the thing. But certainly if there are only 30 some patients, then you don't really have much of a choice. So,
I do think that point about the fact that I think there is something different about the sample that we have in N3C and a consented, highly engaged patient cohort. I think that there's a lot that maybe would speak to the desire to retrain because that cohort is so different. But you're absolutely right that it's not an easy decision.
So Saad Bujoli comment, we're attempting to translate the pregnancy episodes algorithm from N3C to AOU also, so AOU can define pregnancy episodes and use that to perform pregnancy or maternity research.
That's awesome. That pregnancy episode algorithm is incredible work. If you haven't looked at it, it was recently published in JAMIA. Really nice paper, really cool algorithm. And the fact that that's getting translated as well is really wonderful news. So see, we're all getting on board the model sharing train. I hope that we can continue on this path for a long time.
Oh, that's very important. So I have a question / comment. So let's say we were interested in post-viral syndrome for Lyme disease, or EBV or whatever virus you're looking at. And certainly, as one moves to all of us and to data sets that are not as specifically focused on COVID, or to your point, even data sets that are focused on COVID, given ultimately the prevalence of COVID is so high that most people have had it. So if somebody has symptoms consistent with a post-viral syndrome, what are your thoughts about, whether it's possible or even necessarily desirable to call it long COVID versus long Lyme or long anything else? I mean, isn't it really fundamentally you're looking for collections of symptoms that are consistent with a syndrome that could be caused by COVID, but by other things as well?
So I will answer your question with a bit of a stay tuned, because that is actually one of the queries that the RECOVER program is asking this quarter. So RECOVER answers a bunch of queries every quarter. And one of them is, let's take a look at, in this case, post-influenza, prior to the existence of COVID. So let's look historically to see what patients looked like that may have ended up with sequelae of an influenza infection versus what patients look like now with what appears to be sequelae of a COVID infection, and kind of comparing what those look like. Now, I will say that because we have run an experiment, I know that our model identifies people as having long COVID in 2019, which is not possible because there was no COVID in 2019. I suspect that those patients that are getting identified as such have other overlapping conditions, some of which might be these other post-viral syndromes that you're referencing, and some of which may be just other conditions that have overlapping symptoms with what we see in long COVID. So, you know, the nomenclature is complicated, you know, how we refer to these things is complicated. I think we're going to sort out what the differences are between long COVID and long insert other viral disease here, and what the similarities are. And I'm hoping that we'll be able to present to this group if we come up with some interesting results to that question this quarter.
Great. Okay. Well, that's fantastic. Okay. Well, this was great. Any other questions, comments, thoughts? I see a hand. Andrew?
So there is a prediction model library for Odyssey, and I guess I wonder if you thought about, I mean, more strict adherence, I guess, to the OMOP CDM would have prevented some of the translation issues, and registering things in a standard format with metadata in a shareable library is something that can be done with OMOP now. And I wondered if you thought about, I guess, standard transforms that would enable that. I guess maybe I'll note that that's a possibility rather than ask whether it's considered. And then when you're translating something from one site to another, or from one setting where it's been learned to another where you're trying to validate it, there's the option to just see how well it performs, or kind of the idea of retuning it to maximize performance. And I think it's a live question about which is best to do, because it's pretty guaranteed that you're going to get decrements and discrimination and calibration as you go from wherever you've trained to wherever you've learned. And unless you're really attached to the specific thing, you're really mostly interested in the performance rather than in how reproducible it is. And I think that's a live question, because there often isn't a rationale to not recalibrate it and retrain it at the local site so that you can maximize performance. So just your thoughts, I guess, on that as a part of the context for this whole effort, which I think is amazing, and I applaud, and really glad to see your exceptionally lucid presentation of it as usual. But your thoughts on that question?
Yeah, so I think my thoughts are aligned with yours in that respect, that I'm not so attached to the training. Like if you retrain in a different population, I'm cool with that, particularly if there's performance advantages to doing so. Because for me, the model is less the train, and this is coming from somebody who is much more a clinical informaticist than a machine learning expert, right? So coming from that perspective, for me, the real cool part about the model, the unique thing, the thing I want to share, is the structure of the model in terms of the feature engineering. All the feature engineering steps are where all the thought work went in. That's what's important to share. The training step is like the icing on the cake. And if you can use my pre-trained model, wonderful. But if you have to just use all of those feature engineering steps that went into it and then retrain, I think you're still getting the benefit of reproducing the model. And that's why I say, if all of us had more than 30 patients to use as a standard, I probably would have wanted to see what it looked like in terms of retraining. And I hope, all of us keeps growing and keeps getting more longitudinal data. So at some point we will be able to retrain it in there and see what that looks like. And that'll be really cool. In terms of the Odyssey standard library, I was not aware of that. And that sounds really great. And I would be delighted to learn more about that and how we can contribute to that, because that's very aligned with my share early and often kind of goals.
It is. It is. And I'll say one more thing. I think one of the things that seems really cool about it, and especially given that description you just gave of how you see the value, is you said at the beginning, you kind of left it in mind as to what threshold might be useful. I think a lot of times when people are producing prediction models, the best results come when there's a specific decision in mind that's probably got a specific performance criteria. If it's not better at discriminating than people do on their own without the aid of the model, or when you know people above a certain amount of risk really ought to be getting a different kind of care, or something that's fairly specific that a person in a particular role in a particular setting needs the model for. And having that ability to take what you've done and perhaps take the elements of it that are available at a site that has these data elements and then locally recalibrate it for that purpose. It seems like it lends itself to a broad set of real applications, and perhaps some of the additional work is enabling sites to kind of understand feature importance and what can be really run at their site, where those parameters are available, where those features are available, and do that local recalibration. But it's excellent work. Thank you for sharing it.
Yeah, thanks for your comments.
Great. So another question from Liliana Brown: how soon after infection can the model identify people who have long COVID? Meaning, can the model be used for prediction from an acute infection towards long COVID?
Another very important question. So this model is not a predictive model. It was not designed to be predictive. And the reason behind that is that it actually, if you wanted it to be a predictive model, this model cheats, because it looks at data that happens after acute COVID in order to make its decision. And because of that, this model is more appropriately classified as a computable phenotype. It is a model that is intended to retrospectively identify patients who have a condition, as opposed to predicting if they're going to get a condition. You can use similar methods to do the predictive piece, but that is not what we did here. And so we require that people have at least 145 days of follow-up, at least in the version of the model that I discussed today, in order to make a prediction about them at all. Otherwise, the use of the word prediction, I understand, is very confusing in this context, but in order to make a call on whether they are likely to have long COVID or not, we won't even do it until 145 days have passed since acute COVID. It's a little different now, but the premise is the same.
Great. All right. Well, this is fantastic. Any last questions, comments? This is really, Emily, this was fantastic, and it was a great update and really exciting work. So thanks, and see you folks in a couple of weeks. Take care.
Thanks, everyone.